Welcome to the last lesson in this unit of atomic structure. Electron dot diagrams. Well, let me take a step back. Where have we been? We have given full models of the atom. Give me 1 second. That's better. In a full model of the atom, we have the nucleus, and we have all of the shells, all of the energy levels in which we can find electrons. So, for example, if we're talking about sodium, sodium is 281. So we know from this that there are 2 electrons in the first energy level, 8 in the second, and 1 in the third. It turns out that in terms of chemical reactivity, not all electrons are the same. It turns out that the inner electrons, in this case it would be the first shell and the second shell, have structural value, have structural importance. It's only the third shell, in this case the third shell, is only the last energy level. It's only those electrons that participate in chemical reactions. So let me just jump ahead and say this. The electrons in the outer shell are called valence electrons, and these are the ones that participate in chemical reactions. As I said, the valence electrons are the electrons in the outer shell. And it's so easy to recognize that last shell. It's the last number in the electron configuration. Well, you might ask, well, then what does that leave? What do we call those electrons that are in shells that are not the valence shell? Well, we call those kernel electrons. Kernel is actually refers to the center of something. It's those electrons that are around the nucleus. So the kernel electrons are the inner shell electrons. And just to make it crystal clear, excluding the last shell. That's redundant, I realize, but I really want to make the point. So if I ask you, in this particular atom, how many valence electrons are there? Well, you would say there is 1 valence electron. How many kernel electrons? Well, 10 kernel electrons. And of course, when you add up valence plus kernel, you get the total number of electrons in the atom. To give you another 2 examples, oxygen, with an electron configuration of 2, 6, has 6 valence electrons. Again, you merely are reading the last shell. Calcium, with 2882, has 2 valence electrons. If I ask how many kernel electrons does calcium have, well, you just count the electrons in the other shells. 2 plus 8 plus 8, that is 18. Whereas oxygen has only 2 kernel electrons. Now, if I just want to show the valence electrons, I'm not going to write this full diagram. This is what the complete sodium atom in the ground state looks like. But if I just want to talk about those electrons that participate in chemical reactions, well, I don't care about the nucleus, and I don't care about the kernel electrons. The only shell I care about is that outermost shell. So I use something called a Lewis dot diagram just to show the number and arrangement of the valence electrons in that outermost shell, which I've written this way. It shows the number and arrangement of electrons in the outermost shell, and of course, in your configurations, the outermost shell is simply the valence shell. You count up, you look at the number in the outer shell, and you know the number of valence electrons. Well, let me show you now how to write a Lewis dot diagram. I'm actually going to show you 2 ways of doing this. One, the very formal way, and then the second, slightly relaxed, simplified way. Both are acceptable, but I feel that I feel most responsible showing you both. When we write a Lewis dot diagram, we're going to write the symbol of the element. Because this is no element in particular, I'm just showing you how to write them. I'm just going to use the letter X. X is going to stand for the symbol of any element. First of all, I guess I should say this. You can have a maximum of 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, or 8. So what I do first is I imagine that I'm looking at a clock. And the clock is going clockwise, of course. And the numbers, there are 4 positions around the symbol: 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. So what I do first is I will put the first electron at 12 o'clock. And in this formal way of doing it, I also draw the second electron at 12 o'clock. That's just coincidental that 12. This means electron number 1, electron number 2. Now, I can only have 2 electrons in any one place like this. So now I move to 3 o'clock, and I place my third dot. Again, just coincidentally, dot number 3. I then move to 6 o'clock, and I put the fourth dot if I have a fourth valence electron. I then move to 9 o'clock, and I put another dot there. And that would be dot number 5. Now you notice here, I go back up to 12, but there is no place. There's no room left at this position. So I keep going. I go back to 3 o'clock, and now I can put a second dot here, and that would be my 6th valence electron. If I have a 7th valence electron, I move on to 6 o'clock, and I put a 7th dot here. And finally, if I have an 8th dot, which has a special significance, which we'll talk about, I then finish up at 9 o'clock. That would be dot number 8. Let me take you through a couple of examples. So, oxygen. If I say write the electron dot diagram for oxygen, first thing you should do is write the symbol for oxygen. Next, look up oxygen on your periodic table and see how many valence electrons you have. 6 valence electrons, so I'm going to write a total of 6 dots. I start at 12 o'clock, and I put my first dot at 12. And then I put my second dot at 12. I then move on to 3 o'clock and place my third dot. To 6 o'clock, I place my fourth dot. Keep going clockwise, 9 o'clock. My fifth dot. There's no place to put it at 12. I go back to 3, and I put my 6th dot. So my Lewis dot diagram for oxygen is this, this, and this. This has a significance, the fact that these are loner dots, and those are paired up, but we won't talk about that here. Now, I did mention earlier that there's a simplified way of doing this. And let me show you the simplified way. You may just prefer it. What I can just do is just do this. I can just at 12 o'clock, again with oxygen, choose 6. I have 6 dots to place. So in my simplified way, I do this. I put 1 dot at 12, 1 dot at 3, 1 dot at 6, 1 dot at 9, keep going, 1 dot at 12, and 1 dot at 3 o'clock. If you notice, that's the same as my formal approach. Where you would see a difference is in the case of atoms with fewer valence electrons. For example, according to the formal way for carbon, carbon is 2,4. In the formal way, I put the first 2 of the valence electrons at 12, and then I go to 3 o'clock and then to 6 o'clock. In my simplified way, it's going to give a distinctly different dot diagram. Put 1 dot at 12, 1 dot at 3, 1 dot at 6, and 1 dot at 9. The reason this is okay is that this way of drawing it is the normal, the natural. This would be called non-hybridized. And maybe I'm saying this more for the benefit of the advanced topic students. This is considered a hybridized. I won't go into what this word means, but when carbon bonds, the electrons behave as though that they are all single, free, unpaired electrons. When carbon is not bonding, the electrons would be found in this arrangement here. That's why there's really no difference in writing this or this. So at this point, you might just prefer that if I give you, I don't know, phosphorus, you're going to go by the simplified way. You'll say it's 285. You know that there are 5 valence electrons. 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, 12 o'clock. And actually, in phosphorus' case, it doesn't matter. I could also do the formal approach. 1, 2, 3, 4, 5. Again, it's only if you have fewer valence electrons do you see a difference. Generally speaking, you get identical patterns, whether you go simplified or formal approaches. There's one final thing on this page. I'm going to summarize with a contrast. Remember what I first said. If I want to show all of the electrons of an atom in the ground state, I will draw something called an electron shell diagram. So notice here, I have 2 electrons in the first energy level. I have 8 electrons in the second. So notice the arrangement, I'll draw it the same way. Notice we have, again, 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. And then I have 7 electrons in the outermost shell. 1, 2, 3, 4, 5, 6, and 7. Again, this is if I want to draw all of them, because remember, this shell in blue, this is the valence shell. The ones that I'm highlighting in green, the inner shells, are the kernel electrons. But remember, if I only want to see the valence electrons, because those are the only ones that directly participate in chemical reactions, I'm going to draw an electron dot diagram. 287, I have 7 valence electrons. It's going to be the same pattern as the outer shell, the blue shell. 1, 2, 3, 4, 5, 6, 7. And that is the topic, dot diagrams, electron dot diagrams, Lewis dot diagrams, Lewis electron dot diagrams, all synonymous. And that is the unit. Thank you so much. And hop in for my next unit, which would be nuclear chemistry.